So next, let's move on to probably the most common data structure you're ever going to use, whether we're talking about coding interviews or real coding at your job or projects or anything like that. Hash maps and hash sets are really, really useful. And to start with, I'm going to be focusing on the application of these rather than the implementation, because it's much more important to know how to use these than it is to actually implement them. We already talked about sets and maps earlier, specifically the ones that are implemented with binary search trees. Now, I talked about how sets are just kind of a set of values like 1, 2, 3, whereas maps are a little bit more complicated. That is kind of a set of keys, which are then mapped to a different value. We gave the example of like a phone book where some name is mapped to, the phone number 1, 2, 3, something like that, right? So we're primarily going to be focusing on maps because they are generally more common and they're a little bit more complex, but the main ideas behind a map are nearly exactly the same as a set. Instead of just having a set of keys, we're going to have that set of keys, except each key is going to be mapped to some separate value. But the key is what's used to sort the binary search tree. It's also what's used to access values from the hash set or the hash map. First, let's compare tree maps and hash maps though. There are typically three main operations you want to do when you have a map. You want to insert. When it comes to tree maps, the big O time complexity is log n to insert into that tree. That's definitely better than maintaining a sorted array, because inserting into a sorted array in the worst case would be big O of n. Removing from the tree is the exact same. It's also log n. Likewise with searching, we essentially run binary search on the tree map and we can search for any value in log n time. That's pretty good. And there are other bonuses of tree maps because they're ordered. We can iterate through it in sorted order. If we have that tree map, we can iterate through it in sorted order in O of n time. So that's like our in order traversal. Just by having a tree map, we are kind of maintaining that sorted order. With a hash map though, things get interesting. Inserting is actually a constant time operation. Removing is also a constant time operation. And searching is also a constant time operation. So you can already see why hash maps are probably the most useful data structures you're ever going to use. They really just beat tree maps out of the water. But there's a bit of a caveat here that this is actually not the worst case time complexity. Even though I'm writing it as big O, which means worst case, hash maps actually don't have this as the worst case time complexity for these three operations. This is actually the average case time complexity. But the vast majority of the time, people still assume that it is the worst case time complexity. So we write it as big O of 1. Like if you're ever doing a coding interview, it's safe to assume that these operations run in constant time. That's what people assume in jobs and just in general. I think if you ask them, most people don't actually know that these operations are actually average case. In the worst case, inserting, removing, and searching actually could be O of n time, depending on how you implement the hash map, but that's not so important, and we'll actually touch on that a little bit later. Now, the downside of hash maps, and there's always a downside when you have something this good, it's that hash maps don't maintain any kind of ordering, actually. So if you wanted to iterate through all the keys of the hash map, you could not do it in O of n time. You'd basically have to take all of the keys and then sort them, and then depending on what sorting algorithm you use, you could use, merge sort, you could even use a binary tree sort. It would be n log n typically though. So that's sort of the downside, but you can see that the positives definitely outweigh the negatives, especially if you don't need to traverse it in order and you just need to insert, remove, and search, which is what we would probably do with a phone book. Then hash maps are very important. So let's take a look at a common use case of hash maps. Let's say we were given a list of names, maybe in the form of an array, and we want to count for each name, how many times does it show up in this array? So how would we use a hash map to do that? Well, the obvious way would be to map every single name, so use that as the key, and the value in this case will be an integer with the count of that name. So initially our hash map is going to be empty. We start at the first name, it's Alice, so we go ahead and add Alice to our hash map. But before we would even do that, what we could do is run search on our hash map. We would check, is Alice already in the hash map? No, it's not. And remember, search will run in constant time. So it's not in the hash map. So when we do insert it into the hash map, we should put the value 1 because this is the first time we're seeing this name. Next, we would go to the next position. By the way, for us to have done that, for us to have gone through one position, we did it in constant time. If we were doing it with a tree map, in the average case, that would actually run in log n time. I mean, we know that inserting a node into an empty tree is probably going to be O of 1, but in general, it's going to be log n. So now we're going to get to the second name, Brad. We're going to search for it in our hash map. That search is going to be O of 1. It doesn't exist. So we're going to do the same thing with Brad. We're going to add it as a key, and the value initially is going to be 1. We're going to get to the third one. We're going to get to the third name, Colin, do the exact same thing. Colin is also now added to the hash map. The value, the count of it is 1. Now we're going to get to our first duplicate, Brad. We've already seen Brad. So when we search our hash map, we're going to find that it already exists in the hash map. And it's at this position. So instead of assigning 1 here, we don't know. The count could be anything. Right now it's 1, it could have been 2, it could have been 3, it could be some value. We know it's not going to be 0 though. So what we should do here is instead of assigning it to 1, we should add 1 to it, which would put it to be 2. So we overwrite that value with a 2. By the way, doing that, iterating through this position was also a constant time operation. And notice we don't have duplicates in this hash map. I mean, we could have added another entry for Brad and put 1 here, but that isn't what we're trying to do. For Brad, we're trying to count how many times did it show up. It doesn't make any sense to add a second entry. And this brings us to a property of hash maps. They cannot contain duplicates. Duplicates are not allowed in hash maps because it doesn't really make sense for us to do that. That's not the use case for a hash map. Why would we want multiple copies of the same thing? And that's the exact same with binary search trees. Remember, we don't allow duplicates in binary search trees, so a tree map is also not allowed to have duplicates. So now let's go to the next position, Dylan. It doesn't exist in our hash map. We figured that out by searching, which is an O of 1 operation. So we add Dylan to the hash map, and the count is going to be initially assigned to 1. We get to the last person, Kim, and they also are not in the hash map. We add Kim and then set the count to be 1. Now for each position in the input array, we basically did a few O of 1 operations. So that means to have gone through this entire array and built this data structure, it would have been an O of n time algorithm. Now also the space complexity would also be O of n because in the worst case, every single name could have been unique. That would have led the size of our hash map to have been O of n. But this is definitely better than using a tree map. A tree map would have had the same amount of space, roughly speaking, it would have been O of n, but the time complexity for each one of these insertions and searches would have been a log n operation, and we know we have n values in the input, so the overall time complexity would be n log n with a tree map if we were doing it. But now we have a hash map. Hash maps are much more efficient. By the way, the code for this type of algorithm using a hash map would look something like this in Python. Suppose we're given an input array, names, and the same exact names that we have listed up here. We create our hash map. This is how you do it in Python. It's a little bit different than most languages, but in most languages you would declare like a hash map data structure with like a constructor or something like that. We're calling it count map. Then we're going through every single name in our list of names. And remember, we have two cases if count map does not contain this name. Now in Python, the syntax for that is like this: if name not in count map, but most languages will have a count map data structure, and that will have a method or function which is called, let's say, contains, and then you'd pass in this key as the parameter to that method call. But basically we're checking this name does not exist in this count map, therefore we're going to assign that name to have an initial value of 1. The else would be that the name already exists in the count map. Therefore, we would increment that count by 1 like we did for Brad. So it's a pretty straightforward algorithm. It runs in linear time. Next, let's talk about how we can actually go about implementing a data structure like this.